All right, so before we go on with this really elaborate subject, it's remarkable. I'm pouring through the book that I'm using as the model for this, which I'll remind you is Gilmore. It's Gilmore's book, right? I should remind everybody of this just to make sure everybody knows that I'm really not inventing this pedagogy. It's coming from Gilmore's book. The thing is that Gilmore moves quickly through topics. Well, he does a really good job. I mean, it's a difficult balance to get this subject out without going deeper. But I always, in these lectures, just if there's an open question, I go deeper, and that's why you're seeing a lot of topology arise, and that's not going to change. But I do want to step ahead before I go back. We've been talking about homotopy groups, and we've kind of left behind the fact that we're dealing with right now, or where we were left off with studying the special orthogonal group and the special unitary group. And what we had discovered was that we could first of all, we created these matrices. So we know all the elements of this group, and here they are. They're these guys. And we know that there are three parameters that build up these elements. Just as a reminder, right? Theta was a general parameter, and these guys were normalized coordinates. So there are three real coordinates, right? Theta 1, theta 2, and theta 3. They get normalized and compact and sort of thrown into this matrix this way, and then theta is built out of the three of them. I guess I should just write it down instead of talk about it, right? So there's three parameters. There's three parameters that cover this manifold. Three coordinates, right? Theta 1, theta 2, and theta 3. We create this guy theta, and we normalize the coordinates, and they land in this expression this way. Now, this is totally for convenience. I'll remind you, I mean, we're several lectures away from the actual construction of this matrix. But this matrix is completely constructed in terms of theta 1, theta 2, theta 3. It was just notationally convenient to collapse these things into these expressions. Otherwise, you would have this expression here, for example, would be theta 2, theta 3 over theta squared, 1 minus, what would it be? It would be minus cosine of theta 1 squared plus theta 2 squared plus theta 3 squared, right? We would have carried all that crap around. So we simplified it. This is just a reminder for what we did several lectures ago. So we created all the elements of these two groups, right? And they're group elements, so the group operation is mimicked by matrix multiplication, and they all have inverses, and everything is amazing. And what was interesting is we generated both of these groups, remember, from the same Lie algebra, and that's the real point here. The same Lie algebra defined both of these groups. The difference in our analysis that led to this versus this is how we represented the Lie algebra. In this case, we represented the Lie algebra essentially using the Pauli spin matrices, where I use the word spin matrices. We're not talking about spin yet or anything physical, but that's what these guys are called. These matrices are called the Pauli spin matrices, and then we chose our elements of the actual Lie algebra to be written in terms of these spin matrices in the following way. I think we wrote it as x, I think it was I over 2 times the appropriate spin matrix, right? So these were the generators that we used. And then we took a bunch of algebra and we did all these crazy things, and we ended up with this expression for SU2. And for SO3, we used a totally different set of basis matrices that were three-dimensional. They were three-dimensional representation of the same Lie algebra. Where remember, we defined the Lie algebra's ultimate defining quality was its commutation relations, xi, xj, and I think we went with minus epsilon equals minus epsilon I, j, k, x, k, right, with the intentional summation over the k. But with the same commutation relations, we have 3x3 matrices that we used in the case of SO3. I think it was these guys. Let me make sure. I think my signs were right. I always get confused because x2, the way we did it, the sign, the negative sign is up here, but the other one, the negative sign is in the lower part of the matrix, but for x2 it's in the upper part. But I'm pretty sure that's right. You can go back to the previous lectures that we did this on, but I'm quite sure this is it. But these three guys have the same commutation relations as these two, and they represent the same Lie algebra. It's an isomorphic mapping of the Lie algebra. The problem is when you exponentiate it, you get this thing, which is different from this. And that's not in itself a problem, but it's not the same group. These are not the same, they're different. They're different topological spaces, they're different manifolds, they're different groups. So the way we started to study these guys, and you may remember what we discovered when we studied these guys, what studying means looking at it in terms of coordinate space. And so when I say looking at it in terms of coordinate space, what we did is we took these guys and we treated them as manifolds, right? And we figured out how to describe each and every matrix in its own representation in coordinate space, meaning the space of theta 1, theta 1, theta 2, and theta 3. And we discovered something interesting. They don't really have the same representation in terms of coordinates, right? The coordinate mappings give us some very unique differences. And today we're going to show the relevance of, now we are in a position to understand the significance of those differences. And let me remind you what those differences were. I initially talked about I recapped these differences in lesson 33. That was a recap of parameter spaces, SO3 and SU2. So this is a recap of the recap, all right, which never hurts. And I always do it, and that's just the way it is. All right, so you'll remember what we did and recapped back in lesson 33 was we understood that, hey, if we have this group, right, and we've now used our manifold mapping, our pseudo-manifold mapping, which, as I pointed out in lesson 33, right, this coordinate system kind of breaks down at theta equals pi, right? When theta equals pi, we have a problem with this coordinate system. Same will be true of SU2, but the fact is it's still convenient to go with it. But what we noticed was that, well, first we understand that this group maps into this parameter space, this coordinate system, and the origin of the coordinate system is the identity element of the group, right? The identity element of the group. It maps right there to the origin of the coordinate system. So what we learned, though, is that, heck, if we started at the origin and just sort of wander in a straight line out, what we do is we always return to the origin, right? These points way out here always repeat through these various matrices, or all of the matrices that are represented by points along this line segment here between the origin and theta equals pi. I guess I should make a note of that this is here, this would be, anything on that sphere is theta equaling pi. All right, it's a sphere, right, because theta 3 comes out. That's what this means here. Theta 3 is coming out of the board. Theta 1 is this sort of x-axis, and theta 2 is sort of this y-axis. So what we did was we said, all right, well, forget all the points out here. We'll just understand that only all of the points inside a sphere of theta equal pi, that's all we need to consider, because that captures every element of the group. But we do notice a problem at theta equals pi, right? We studied this pretty carefully, and just to recap, let's see if I can recap it effectively. When theta equaled pi, all of the sine terms are 0, right? When theta equals pi, the sine terms are all 0. And the cosine terms are, what were the cosine terms? I guess the cosine terms, of course, were -1, right? So this becomes a -1, -1, -1. The 1 minus cosine terms, those become 2, right? So they all become 2, right? And that kind of left us with a matrix that is really all about the direction that you're headed in. So if you are at theta equals pi, what that means is that you're on this sphere somewhere, right? You're somewhere on this sphere. where you exactly are depends on the specific values of theta 1, theta 2, and theta 3. And each of those points on the surface of the sphere will have its own matrix defined by theta 1, the value of theta 1, theta 2, and theta 3. So every point on the sphere has essentially a different matrix. It's just the problem, though, is that that's not exactly correct, right? Because if I pick the value theta 1, theta 2, and theta 3, and I calculate the matrix for that value, right? It'll be a 3 by 3 matrix. If you study this very carefully, you'll realize that if I picked minus theta 1, minus theta 2, and minus theta 3, I get the exact same matrix, right? So these coordinates here and these coordinates here give me the same group element, right? And that was the problem, right? Because that shouldn't be true for a manifold, but we are using this coordinate system conveniently anyway. I mean, it is a manifold. Don't forget that. It is a manifold. We're just going to jam everything, though, into one chart. And the price we pay is redundancy. This point here with theta 1, theta 2, and theta 3 is going to be exactly the same matrix as that point there. These points are identified. These points are identified. And so if I wander off in this direction along the in the parameter space, I emerge here, and if I keep going, I eventually come back to the identity. And that is why this is a compact space, right? This is compact because you always return to the identity as you wander through the space. And that doesn't matter. It doesn't matter what direction you go. If I go here, I end up with a different matrix here, right? The matrix at that point is not the same as the matrix at that point, but I do return to the identity this way, right? So the opposite points on the sphere are identified. And what's important to understand is when we talk about points being identified, right? If I put that, I guess in sort of in quotes, say, if I use this word identified, what I'm really saying is that this point and this point are actually the same point. We're going to bottle them up in this small, as the same place. If I am standing here, I am also standing there, right? That's an important part to understand. And when I leave this point, I can leave by going back inside the sphere, or I can leave by going back inside the sphere this way. It's all the same because the 2 points are literally identified. So we studied that and we recapped it in lesson 33. What we also did is we did the same analysis for SU2, but we ended up with a very different conclusion. In SU2, we used the exact same coordinate system, right? It's got the same concept that the identity is mapped to the origin, just like before. But now what we did is when we said, well, wait a minute, what gives with this sphere? And in this case, the curiosity occurs at 2 pi, right? When theta equals 2 pi, right? Then we look over here at the matrices for theta equals 2 pi, and we discover, well, what's going to happen in this case? Well, sine of 2 pi over 2 is going to be the sine of pi. So these terms are all going to be 0. And then the cosine of 2 pi over 2 is the cosine of pi. So these guys here will be -1, will be just -1 and -1. So that means that everywhere on the surface of the sphere, the entire SU2 matrix breaks down into, let me make my tip a little finer here, -1, 0, 0, -1, which equals minus the identity element. And now you'll notice there's no theta 1 hats, theta 2 hats, or theta 3 hats in the matrix at all. It's just -1, -1. That's the whole matrix, which means that whenever theta equals 2 pi, the element that it's referring to in the group is always going to be opposite of the identity. So now understand we have this topological space, which is also a group, right? That's the whole beauty of this thing. There is I, but then there's also minus I, right? Man, why did I make minus I? Why don't I make that a different color? No, red is fine. Red is actually fine. Minus I is a point. But what's interesting is that, in this sort of dysfunctional coordinate system or overstressed coordinate system, the entire surface of the sphere is the same point. Here it was kind of weird because we were identifying points opposite of the sphere. That seemed weird enough. But here, the entire sphere is a single point in the group. And so the implication here is that no matter what direction you wander off in, eventually you'll hit opposite of the identity. And once you're there, it's not that you come back here and keep going back towards the identity. You're essentially, although in principle you could, right? If you kept going, you would end up right back at the identity. If you kept going sort of out here in the parameter space, that's equivalent to starting back here and going to the center, just like it was here, right? In this case, the antipodal elements are the same. That's also true here. Antipodal elements are the same. The problem is every element on the sphere is identical. At least this antipodal element was different from, say, this one or this one or this one or this one. They're all different, right? But in the sphere, not only are the antipodal points identified, everything on the sphere is identified. So just like once I hit the sphere, I'm actually allowed to start wandering back in the sphere from any point on the sphere, right? Any point at all. So this was fundamentally different about the two. And how do we know that this difference is relevant? Well, that's where, now we've reviewed this, now we can actually see that clearly this has something to say about paths inside this topological space. This topological space, which is essentially equivalent to this, right? Because we have all of this beautiful mapping, and once we understand about the nature of the sphere, we've got it totally under control. So when we think about the topological space of SO3 and the topological space of SU2, right? SU2, we can study it through the coordinate system. That's because it's a manifold. So when we do that, we learn something really, really important. All right, so here are our two spheres, right? This first sphere, well, the sphere on the right, I'll say, is SU2, the sphere for SU2, and this will be SO3. Now, the difference is this sphere, of course, they both have theta 1, theta 2, and then theta 3 is always coming out of the whiteboard. This guy here, that's 2 pi, right? That's 2 pi for SU2, and it's pi for SO3. But that's really not so important. Now we're going to actually talk about the homotopies of the different homotopies for these two groups, right? Or for these two topological spaces. And then I fall into this trap too. SO3 and SU2, we are now considering them as topological spaces, right? That's really tricky because the elements of this group, right? If I go to, say, some point here or some point here, that's a coordinate. And from this one, I get a 3 by 3 matrix, right? And from this one, I get a 2 by 2 matrix. And that represents an element inside the group, and I can multiply it by another element inside the group, and I can get a third element inside the group. And then, of course, we know that the center of the group is the identity. That's true in both cases. And these matrices represent the group elements of SO3 and SU2. But right now, we don't care about that. We don't care about the fact that the points in SO3, the points that are tagged with the coordinate system that's given to us by the manifold structure, right? We don't care about that, the fact that those points are group elements. Right now, all we care about is the topological structure of the manifold that is SO3 and the topological structure of the manifold that is SU2. So we're now going to look at paths inside these two topological spaces, and those paths are going to start at the origin, right? They're going to start here. Oh, that's a little bright. So there are paths that start at the origin and end at the origin. Now, we already know that if I create a loop inside a topological space that starts and ends at one point, as long as the space itself is path connected, meaning any point in the space can be reached by any other point through a path, then the fundamental group that I discover by studying paths that begin and end at a certain point will be the same for any point. So I can speak about the fundamental group of the whole space just by studying it at one point, as long as the space is path connected. So I've already drawn one conceivable loop in the space of SU2, right? This is the loop that leaves the origin and comes back to the origin. And it never touches the sphere, right? It never touches the sphere. And it's pretty clear that this loop can be continuously deformed into the constant loop, right? As can, say, this loop. Well, I should draw it. As could, say, this loop, right? I could do some really tricky thing, right? And then come back to the origin. And that loop can be continuously deformed into a constant loop that never leaves the origin. So both of those loops are members of the homotopy class of loops equivalent to the of loops that are equivalent to the identity loop, or the constant loop, I guess is the way to say it. So the constant loop, its equivalence class is indicated by this. I use these little funny double braces. That is the set of all paths that are equivalent to the constant loop. Now notice I said all paths, I used the word equivalent. I said all paths equivalent to the constant path. Equivalent, when I say that, I mean homotopic. And homotopic, as we've shown, is an equivalence relation. So I can use, the equivalence is homotopy equivalence. So this represents the set of all these paths that are loops that can be redeformed into the constant loop. And that equivalence class is going to be one element of the fundamental group of SU2. Now, clearly, I can do the same thing over in SO3, right? I can make a loop that looks like this, and I can make a loop that looks like this, and both of those loops are also homotopically equivalent to each other and homotopically equivalent to the constant loop that never leaves the origin. So SO3 also, in its fundamental group, it has the same equivalence class of loops that are the constant loop. See, so the way I'm going to do this is I'm going to erase this. You understand that those double brackets mean an equivalence class, right? So this is going to be the set. This is going to now be the fundamental group of SU2, right? It's a set, and the first element in the set is the equivalence class of all paths that are equivalent to the constant loop. And then over here, I do the same thing. So in both cases, we've definitely found at least one equivalence class. So now let's look for another equivalence class. So let's go back to SU2, and we say, all right, well, certainly we've covered all of these loops that kind of fool around in here. That looks very much like the unpunctured plane. But we do have this sphere. We didn't touch the surface of the sphere. So now we go out and we connect with the surface of the sphere. So what happens now? Once you touch that surface of the sphere, it's really weird because you exist everywhere at once, right? The surface of the sphere is a single point. It's all identified as a single point, which means once I touch the surface of the sphere, I can continue that path starting or continuing from any point on the sphere. Like I can pick this point, and then I can come back, and now my path is continuing. Now I need to make a loop. So this path has to end at the origin, right? So there we go. So there's another possible path in SU2. And this could have been anything. I could have come in from this point if I wanted to. I could have come in from this point if I wanted to. I could have come in from this point if I wanted to. I could have come in from any of those points. Or I could have touched the sphere and then come back, right, if I had wanted to. I could do any of those things. And maybe by looking at the fact that you could do any of those things, you can kind of see what this implies for the homotopy of this path. So I'm going to draw it like this, where we leave on that, We leave outbound on that first quadrant path, and we return inbound on this fourth quadrant path, right? Remembering that this is a sphere, by the way, right? This is a sphere, but we're just going to look at it in cross-section without any loss of generality. So what is this path homotopically equivalent to? Well, it's certainly homotopically equivalent to this path, right, where I go out and then come back in here. And that is certainly homotopic to this path, right, where I go out and come in here, because all I'm doing is I'm smoothly moving this portion of the path. I'm homotopically and continuously deforming it into this portion of the path. And I'm allowed to move anywhere on the sphere, so that's not a problem, because that point is equivalent to that point. So I move this point along, and eventually I'm going to bring this point all the way over to here until I'm returning. This is a return, that's a return, that's a return. Eventually I'm returning from right here. And eventually, of course, I'm going to bring these 2 points together into a single point. So now I'm kind of going out, touching the sphere, but then leaving the sphere right away and coming back. And then what happens next? Well, now I just detach from the sphere, and I go out, detach, come back, out, detach, from back. And I have a path that's homotopically equivalent to the constant path. So if I touch the sphere, that doesn't really affect the fact that my path is homotopic to the constant path, because I can always deform it back into the constant path. So touching the sphere once doesn't matter. And the reason it doesn't matter is because I can always take this point, move it to that point, and then detach and come back to the origin, right? So because I can always do that, touching the sphere doesn't matter. Well, that was touching the sphere. But let's take a look, on the other hand, over here in SO3, right? So now I follow a path, and I come, say, to this point. Now this point is identified not with the whole sphere, but only with the point that's exactly opposite. So if I wanted to continue this path, one option is to touch the sphere and then come back, right? And in that case, I haven't really punctured the sphere, right? I just touch it and come back. So I can detach, and I can then see that once I've detached, it's equivalent to the constant path. The problem is not when I touch the sphere and return immediately. It's when I touch the sphere, take advantage of the fact that I'm identified antipodally, and then I keep going and return this way. Now there's an issue. Because now how can I deform this path? Well, I can certainly, starting from this antipodal point, I certainly can deform this path any way I want inside the sphere, right? I can certainly make this deformation or that deformation or that deformation. Those are kind of uninteresting, right? But those are obviously all homotopic. But what if I try to say, okay, I'm going to take this point, I'm going to move it like that. I'm going to homotopically and continuously move it, because each one of these points is different. It's a different group element. It's a different point in the space. Over here, all of these points were the same element in the topological space SU2. Here, all those points are different. They are identical to the equivalent points on the other side of the sphere, right? Well, I guess that'd be here, right? They're identical to those points, but they're different from each other. So if I tried to homotopically move this point here down the surface of the sphere, hoping to maybe catch up, the problem is that as I do that, if I were to homotopically deform this part of the path like this, I'm compelled to homotopically deform this part of the path like that, because these points have to always be antipodal to those points. So I can never take this point and move it along the sphere and catch up with these points, connect it, and then detach and show that I'm homotopic to the constant path. I was able to do that here. Here I can just independently move, because all these points are identical. I can just independently move it, connect it, detach it, and boom, we're back in the constant path. But here you can't do that. So this path is actually, if you hit the sphere and then you come back to the origin after crossing to the antipodal equivalent point, that path is not deformable to the constant path. So I've created a new, or I've discovered a new homotopy class. And I'm going to call that new homotopy class 1. It's 1 because it touches the sphere once. So right away, something's fishy, right? Something's fishy right away because these two groups, which had the same Lie algebras, we constructed them using very similar methods, but we used different representations of the Lie algebra. Here we use the two-dimensional representation. Here we use the three-dimensional representation. That led to two different topological spaces, topological matrix groups. Well, it led to two different topological matrix groups, and we've just discovered that it looks like one of them has a fundamental group with two elements, and so far the other one has a fundamental group with just one element. The question is, can we find other elements to this fundamental group? Well, there's not too many choices, right? Because you could imagine, let me erase this. You could imagine something different happens if you go out to the surface of the sphere, reemerge from some arbitrary point, and then wander back into the surface of the sphere again, and then say reemerge, and then maybe you don't hit the identity, but you go to the surface of the sphere again, and then you reemerge, and then you finally hit the identity. You do it several times. The problem is I'm not going to work it out too much, but look, this part here, right, I can just homotopically move that point to this point and homotopically close that loop. So this guy ends up homotopically equivalent to, just one point. And when I do that, I just detach the point, and now this whole part of the loop is gone, right? So that whole piece is missing, is now I've just homotopically eliminated it. As long as there's 2 points, I can homotopically eliminate it without any trouble. And then I do the same thing for this, right? I take this and I just close it up until it becomes a single point, and now that's detached. And then what have I finally got? Well, I finally have sort of this whole thing, and then I bring those two together and they're detached, and then I finally get something that's equivalent to the constant path. So no number, it doesn't matter how many times you intersect, the surface of the sphere during your path. You can always take it and deform it into the constant path. So there's nothing else. My imagination isn't enough to find anything else. And there's formal methods, I presume, out there that lock this down, but there's only one path in SU2, one loop in SU2. Every loop in SU2 is homotopic to the constant loop. And we can now close the fundamental group. So the fundamental group of SU2 has one element, and that's the equivalence class of all loops that are homotopic to the constant loop, and there's no other loops, right? And using the concatenation of loops, right? The way we did this is the equivalence class of a loop alpha, group operation, the equivalence class of a group beta is equal to the equivalence class of whose representative is the loop alpha followed by, or alpha following beta, right? Something like that. So that's the group operation from our nature of what the fundamental group is. But the fundamental group for SU2 is trivial, and it's isomorphic to the identity group, just the simple group with just the identity in it. So now we got to go to SU2 and ask sort of the same, SO3, and ask the same question. That question being, well, what happens if you do this twice, right? What happens if I leave the origin, head up here, and I have to emerge antipodally, so I have to emerge there. But once I'm in here, I can wander around and then say I hit this point. Well, I have to emerge antipodally, which is, let's see, I guess that would be, well, almost, let's say right here. And say the loop completes, I keep erasing things here on this new pen of mine. And then this comes in and comes back to the origin like that. So we leave this way, we proceed around this little thing like this, and we come back into the origin over here. So now what gives? how can we deform this guy? Well, we know that we can move these points that are on the sphere homotopically. We just have to make sure that the opposite point moves with it, right? That's why they can never catch up. This point here can never catch up to that point there, because as it homotopically is moving along the surface of the sphere, this one's homotopically has to move the other way because they're the same point. They're identified in that fashion. But I can move this point towards this point without any trouble. In particular, I can move this point towards this point without any trouble. So you can easily imagine me doing that. Say I took this point and went and brought it all the way to that point. As I did it, this point has to move to this point. So that part, I'll do that in blue, right? This part of the path becomes more and more like this, right? Until finally it's all at one point. And this part of the path becomes more and more like this each time until it finally touches there. And now I have one point here and one point there, and the loop is actually doing this. We're going out and then back. And so I can detach now, because this stuff's all gone. It's all just one point, which is the same as that point. I go out, touch the sphere, and turn around and come back. So I can detach, and then that becomes homotopic to the constant loop again. So what's interesting about SO3 is if I touch the sphere once, I'm no longer homotopic to the constant path. But if I do it twice before returning to the origin, like this, out, so there's my first contact. Remember, when I say once, hitting the sphere once and popping antipodally, that's one contact, because that point and that point are the same. It's identified. So I go out, hit the sphere once, hit the sphere a second time, and come back. The fact that I've hit it a second time, I can use that to close up the loop. And it's really ingenious like that. So if I do this twice, I'm homotopic to the constant path again. And it turns out if I did it 3 times, I could take the first 2, close them up to be something homotopic to the constant path, but I can't clear out the third one. So I'm left over with an element that's homotopic to a path that intersects the sphere once. If I do it 4 times, I can clear that one up, and I'm back to the constant path. If I do it 5 times, I'm back to a path that hits the sphere once, or homotopically equivalent to that. And there's where my imagination runs out, and I'm done. And the fundamental group of SO3 has 2 elements, and it's isomorphic, kind of obviously, I think, to the group with the identity element and minus the identity element, right? So meaning that if I take the equivalence path of paths that have one intersection, say, and then I multiply that by itself, meaning I find the equivalence, I do one path followed by another path, right? So the group operation, one homotopic to a path with one intersection, group operation times the same element, I get the constant element, right? I get the constant path equivalence class back. So it's when I talk about the elements of the fundamental group, the elements of the fundamental group are literally these equivalence classes of paths. It's a group, so there has to be a group operation between this equivalence class and that equivalence class. And we know how that group operation works, right? That, just as a reminder, the equivalence class of group the equivalence class of all paths that are homotopic to a path alpha, the group operation times the equivalence class of all paths that are homotopic to beta, that's equal to the equivalence class of all paths that are homotopic to the path alpha followed by, or the path beta followed by the path alpha, meaning beta first followed by alpha, meaning you follow the beta loop and then you follow the alpha loop. That equivalence class, the equivalence class of that loop, right, of that loop, is what we mean by the operation of the equivalence class of A times the equivalence class of B. I think we discussed that in our last lecture. The point is this group is ultimately isomorphic to the group that contains just the identity and minus the identity. Just like this group is isomorphic to a group that contains just the identity. Anyway, the point is we've now discovered that the fundamental group of SO3 and the fundamental group of SU2 are not the same. They're not the same. When the fundamental group of a topological space is just the identity, that group is called simply connected. When the fundamental group is I minus I, we call that doubly connected. Right, doubly connected. Doubly connected is kind of fascinating, right? Because remember, the plane itself, right? The plane itself with a hole in it, I guess the regular plane, that's clearly the fundamental group is I. All loops in the plane are homotopic to the constant loop. When you throw one little hole in it, all of a sudden, we studied this last time, that fundamental group became equivalent to the integers, right? The number of orbit, you have as many homotopy paths as number of times that you can kind of go around this hole. So something as simple as puncturing the plane gives you a group that is infinitely more complicated than the fundamental group associated with the topological space SO3, which has just got two elements. So being doubly connected is actually, to my taste, is a bit unusual, because to me, this is like the next step in complexity from the simply connected plane, is the plane with a hole in it. But there is this intermediate thing of the sphere with antipodal points identified. That's a topological space. In fact, it's a manifold, and it has a fundamental group of just two elements. Okay, so the point is now we've discovered that being the case, the fact that these two fundamental groups are different, SO3 as a topological space is not homeomorphic to SU2. These are different topological spaces, and that's a big deal. So ultimately, the issue is, if we consider this the topological space of SO3 and the topological space of SU2, that means that the points inside this space are matrices. They're 3 by 3 matrices. Fortunately, because it's a manifold, it can be organized in a way that creates a very easy to understand topological space that we kind of studied today through its coordinates, right? Its coordinate system. And we did the same here for SU2. What we discovered is that SO3 has the property, an associated property, because it has an associated group called the fundamental group, which was I and minus I. Likewise, SU2 had a fundamental group that was trivial. So therefore, SU2 was simply connected. SO3, it turns out, because of this, is doubly connected. The big important takeaway here is that you might think that there's some mapping from SO3 to SO2, that for every element of SO3, there's an equivalent element of SU2. And there's two different kinds of mappings that could go from SO3 to SU2. One type of mapping treats each of these elements in here as a group element of SO3, and it discovers another group element of SU2 that is equivalent, is mapped. It's a mapping that might take an element of SO3 and find an element of SU2. And indeed, there is such a mapping, and that mapping is called now watch the word, it's a homomorphism. Morphism. Homomorphisms are mappings between groups, and there's definitely a homomorphism. However, SO3 is, in addition to being a group where the elements are matrices, in addition to that, and SU2 being a group where the elements are two by two matrices, it's also a topological space. And a topological space might have a mapping as well. And that mapping, we could call that mapping, say, lambda. You might think that such a mapping exists. And sure enough, there are mappings between SO3 and SU2. But none of the mappings are continuous one-to-one on-to with a continuous inverse. It doesn't have any homeomorphic mappings. and I'm putting it up here because I don't want these words to confuse anybody. Homomorphic mappings are between the group SU2 and the group SU2. I'm sorry, the homomorphic mapping would be between the group SO3 and SU2. Homeomorphic mappings are between the topological space SO3 and the topological space SU2. We talked about this in our last lecture. This you just know from elementary group theory. But both of those things could exist in this case because it so happens that this topological space and this topological space are also groups. But on top of that, as a topological space, there's another associated group that's connected to it, and that's the fundamental group, which is unrelated to SO3 and SU2 as a group themselves, as far as we know. Meaning there is a connection between these fundamental groups and these structures as groups. There is a connection. Well, actually, let me strike that. In the next few lectures, what we're going to talk about is the connection between these fundamental groups here and the connection between these two topological spaces. It turns out that this is a simply connected topological space. This is a Lie group that is doubly connected topological space. But they both share the same Lie algebra, right? We know that. So it turns out that there's only one simply connected Lie group that shares a Lie algebra with a lot of other Lie groups, and those Lie groups are not simply connected. Those Lie groups have more complex fundamental groups. And there's a relationship between this fundamental group, the different fundamental groups, and the simply connected Lie groups. And we're going to discuss that. Now, Gilmore talks about it, and he spends a lot of time on it, actually, but he really doesn't dig into why it is. There's a lot of theorems that he states without proof that I find a little disturbing, and we're going to actually walk through this whole thing, and we're going to study the topology of what's called covering spaces. The topology of covering spaces ultimately is going to lead to the language that SU2 is the universal covering group of SO3, or the universal covering space of SO3. And that's going to be a long haul, but I wouldn't be doing justice to my purpose here, which is to sort of fill in the blanks if we didn't. And like I said, since I'm in no rush, we're just going to keep going slow and steady. Okay, so our next set of lectures is actually going backwards a little bit. We're going to talk more about topology and the topology of covering spaces. So the lectures are now going to get a little bit heavy into topology, but we've already started that anyway with our review of continuity and homeomorphic mappings. Okay, so I'll talk to you next time.